In 1964, a Soviet astrophysicist named Nikolai Kardashev proposed something that fundamentally changed how scientists think about the long-term future of intelligent life. He suggested that any civilization anywhere in the universe could be measured not by its culture, its politics, or its history, but by a single variable: how much energy it can harness and use. That idea became the Kardashev Scale, and it remains one of the most useful frameworks scientists have for thinking about the trajectory of technological development, including our own. The scale was originally straightforward. A Type 1 civilization controls all the energy available on its home planet. A Type 2 civilization controls the energy output of its parent star. A Type 3 civilization controls the energy of an entire galaxy. These were not arbitrary categories. Kardashev chose energy because energy underpins everything. Every technology, every computation, every form of transportation or communication, every act of engineering, all of it requires energy. The more energy a civilization can access, the more it can do. There is a direct and unavoidable relationship between energy availability and technological capability. What makes this framework genuinely interesting is where humanity sits on that scale right now. Despite everything we have built, despite the internet, nuclear reactors, space telescopes, particle accelerators, and gene editing tools, we are not yet a Type 1 civilization. We do not come close. We are, by Kardashev's original definition, a Type 0. We consume only a tiny fraction of the total solar energy that reaches our planet, and we have not yet unified our energy infrastructure at a planetary scale. The physicist Michio Kaku has refined this classification with a numerical scoring system. On this scale, a Type 1 civilization scores exactly 1.0. Earth currently scores approximately 0.73. We reached an average global power consumption of roughly 18.4 terawatts as of 2018. That sounds like a large number, but compared to what a fully Type 1 civilization would use, it is negligible. The total solar energy intercepted by Earth's surface is approximately 170 quadrillion watts. We are using a small fraction of what is freely available to us. Kaku has also estimated the timeline for reaching Type 1 status. If humanity increases its energy consumption by roughly 3% per year, a rate that has historically been consistent with economic and industrial growth, we could reach Type 1 within 100 to 200 years. That is an eye blink in cosmic time. Within just a few generations, if current trends continue, and if we do not collapse our civilization through war, environmental destruction, or resource exhaustion, we could cross that threshold and become, for the first time in our history, a genuinely planetary civilization. But what does a Type 1 civilization actually look like in practice? The defining characteristic is complete mastery over planetary energy. A Type 1 civilization would extract energy not just from fossil fuels or fission reactors, but from the full available solar flux reaching its planet. It would harness geothermal energy at a global scale, tapping the heat generated by its planet's core. It would manage its atmosphere and weather with the same confidence that we currently manage electrical grids. Earthquakes, volcanic eruptions, hurricanes, these would be forces that a Type 1 civilization could either prevent or redirect. Type 1 civilizations would also be interplanetary. They would have established permanent, self-sustaining presence on multiple worlds within their solar system. The civilization would have a unified governance structure of some kind, not necessarily a single global government in the traditional sense, but a coordinated framework capable of managing interplanetary trade, communication, and joint scientific research. Medical technology at this level would likely eliminate most known diseases. Human lifespan would be substantially extended, possibly through genetic engineering, nanotechnology, or regenerative medicine. The species would be technologically augmented, but not invulnerable. A Type 1 civilization is still susceptible to extinction from existential threats it cannot yet control. The leap from Type 1 to Type 2 is orders of magnitude more dramatic. A Type 2 civilization does not simply use more energy, it uses a categorically different source of energy. The defining technology associated with Type 2 is the Dyson Sphere, a concept first formally proposed by physicist Freeman Dyson in 1960. A Dyson Sphere is a megastructure built around a star to capture its energy output. In its most complete form, it would be a solid or semi-solid shell enclosing the star entirely, intercepting virtually all of its radiated power. The energy output of a star like our Sun is approximately 380 septillion watts. That is not a number that has any intuitive meaning at human scale, but it represents an energy budget so enormous that a civilization with access to even a fraction of it could do things that seem physically impossible from our current vantage point. Building a Dyson Sphere would require dismantling entire planets to obtain the raw material needed for construction. The engineering challenges involved are staggering. Structural stability, thermal management, communication systems, orbital mechanics, all of these would need to be solved at a scale we have never attempted. It is not a project for a civilization that has barely reached Type 1. It is the defining achievement of a civilization that has spent thousands of years consolidating its mastery of physics and engineering. A Type 2 civilization would have other capabilities that follow naturally from access to stellar-scale energy. Interstellar travel becomes practical, not because physics changes, but because you have enough energy to actually do it. At sufficient energy levels, you can accelerate spacecraft to meaningful fractions of the speed of light, establish colonies in other star systems, and maintain communication networks across distances that currently seem impossibly vast. A Type 2 civilization is also capable of stellar engineering, deliberately modifying the behavior of stars to extend their lifetimes, adjust their output, or use them as fuel sources in ways we have not yet imagined. There is an astronomical observation that has fueled serious scientific interest in the question of whether Type 2 civilizations might already exist somewhere in the galaxy. In 2015, the Kepler Space Telescope detected a star approximately 1,470 light-years from Earth in the constellation Cygnus. Officially designated KIC 8462852, but widely known as Tabby's star, after astronomer Tabetha Boyajian, who led the research team, this star exhibited brightness fluctuations, unlike anything astronomers had seen before. Most stars that dim periodically do so in predictable, regular patterns, caused by orbiting planets passing in front of them. Tabby's star dimmed by as much as 22% at irregular intervals, with no clear repeating cycle. No natural explanation proposed in the immediate aftermath of the discovery fully accounted for all the observed characteristics. Swarms of comets, rings of dust, orbiting debris fields, all of these were considered, and none of them perfectly fit the data. Some researchers raised the possibility that the dimming could be caused by structures built by an advanced civilization, a partially completed Dyson Sphere, or a collection of solar energy collectors orbiting the star in a complex, irregular pattern. This hypothesis was never the leading scientific explanation, and subsequent analysis of the star's long-term brightness history pointed more strongly toward dust as the likely culprit. But the scientific process around Tabby's star was important. It demonstrated that when we look for signs of advanced civilizations, we now have theoretical frameworks for what those signs might look like, and we have observational tools sensitive enough to potentially detect them. The search for technosignatures, measurable signals that indicate the presence of technology rather than purely natural processes, has become a legitimate area of astronomical research. A Dyson Sphere, or even a partial Dyson Sphere, would have a distinctive infrared signature. The star's light would be partially absorbed by the megastructure and re-emitted as heat radiation. Several large-scale surveys have searched for this pattern in astronomical data, so far without a confirmed detection. But the searches have also been limited in scope, and the universe is extraordinarily large. Moving to Type 3, we encounter a civilization that has extended its reach across an entire galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars. A Type 3 civilization has not merely visited these stars, it has colonized them, engineered them, and is actively harvesting energy from them at galactic scale. The power available to such a civilization is incomprehensibly large. Total stellar output across the galaxy runs to numbers so large they become meaningless without context. The key point is that a Type 3 civilization has access to energy reserves that dwarf what any planetary or stellar civilization can access by factors of billions. At this level, the civilization can reorganize matter and energy on galactic scales. It could construct artificial planetary systems optimized for specific purposes. It could redirect the orbits of stars. It could potentially initiate or suppress star formation. The relationship between such a civilization and the raw physical structure of its galaxy would be something like the relationship between a modern city planner and a patch of land. The underlying material is still there, but it has been shaped and organized according to deliberate design. Type 3 civilizations would also confront challenges that smaller civilizations do not face. Stars have finite lifespans. The galaxy itself evolves over time. Red dwarf stars will continue burning for trillions of years, while massive blue stars burn out in millions. A civilization managing an entire galaxy's energy budget would need to think on timescales that make recorded human history seem like a rounding error. Long-term stellar husbandry, deliberately managing stellar populations to extend the useful life of the galaxy as an energy source, becomes a plausible concern. Fermi's paradox becomes especially sharp when you think about Type 3 civilizations. If they are possible, and if the universe is old enough for them to have developed, then a Type 3 civilization should have had time to make its presence obvious. The galaxy is approximately 13.6 billion years old. Complex chemistry began forming much earlier. There have been billions of years during which an advanced civilization could have expanded, built megastructures, and left signals detectable across galactic distances. The fact that we see no such obvious signals is genuinely puzzling, and it drives a significant amount of research and theoretical work in astrobiology and the search for extraterrestrial intelligence. Some proposed solutions to this puzzle are optimistic. Perhaps intelligent life is genuinely rare, and we are simply one of the first civilizations to reach our current level of development. Perhaps Type 3 civilizations exist, but have chosen to remain quiet, or have developed in ways that produce no detectable signatures. Perhaps the physical constraints of the universe make galaxy-wide expansion harder than it looks in theory. Other proposed solutions are considerably less comfortable. Perhaps there is some consistent barrier that civilizations hit as they advance, a great filter that prevents most from reaching Type 3. If that filter lies ahead of us, rather than behind us, if we have not yet encountered the obstacle that destroys most civilizations, then our future prospects are significantly more concerning. The nature of that potential filter is unknown. It could be ecological collapse, nuclear war, artificial intelligence that becomes unaligned with its creators, or some technological risk we have not yet encountered. The existence of this theoretical barrier is one of the reasons the Kardashev Scale, which might otherwise seem like an optimistic roadmap, also carries a darker implication. Getting to Type 3 is not guaranteed, and the obstacles along the way may be severe. Beyond the original three-tier Kardashev framework, some scientists and theorists have extended the scale to accommodate possibilities that go beyond what Kardashev originally considered. These extensions are more speculative than the original framework, but they are grounded in physics concepts that are at least theoretically coherent. A Type 4 civilization would control the energy of an entire universe. This requires accessing not just the energy radiated by stars, but the total energy content of space-time itself. Concepts like dark energy, the mysterious force driving the accelerating expansion of the universe, would presumably be within the technological domain of a Type 4 civilization. The energy available at this scale is so enormous that even describing it in familiar units becomes unwieldy. The implications of such control are profound. A Type 4 civilization would not just observe cosmological processes, it would participate in them. It could potentially influence the large-scale structure of the universe, affect the rate of cosmic expansion, or manage the distribution of matter and energy across intergalactic distances. Whether any of this is physically achievable is an open question. The physics of dark energy is still poorly understood, even at a theoretical level, but the framework gives us a way to think about what the ultimate ceiling of technological development might look like, if there is one. Type 5 and Type 6 civilizations, as they have been described in extended Kardashev frameworks, involve control over the multiverse and over the structure of space-time itself. These ideas draw on theoretical physics concepts, including string theory, the many worlds interpretation of quantum mechanics, and various proposals for extra dimensions of space-time. Whether the multiverse exists as more than a theoretical construct is an active area of debate in physics. There is currently no direct experimental evidence for parallel universes, and some physicists argue that the concept may be untestable in principle. That does not mean these ideas are dismissed, but it does mean they sit in a different category from the more empirically grounded parts of the Kardashev framework. What the extended scale does usefully is highlight the relationship between energy, information, and physical law. As civilizations advance, they do not just use more energy. They develop deeper understanding of the physical principles that govern how energy behaves. Each level of the Kardashev scale corresponds not just to an energy budget, but to a qualitative leap in scientific and technological capability. Getting from Type 0 to Type 1 requires mastering planetary scale, engineering, and global energy systems. Getting from Type 1 to Type 2 requires solving the engineering problems associated with megastructures in space and interstellar travel. Getting from Type 2 to Type 3 requires developing technologies for managing entire stellar populations over geological timescales. Each step involves not just more energy, but fundamentally different physics applications. This is one reason why the Kardashev scale remains scientifically relevant, even as physicists continue to debate its upper reaches. The lower end of the scale, types 0 through 3, involves physics that we already understand well. We can calculate what would be required to build a Dyson Sphere. We understand the energy output of stars. We know the approximate number of stars in the galaxy. The engineering challenges are enormous, but the physical principles are not mysterious. This makes the lower tiers of the Kardashev scale genuinely predictive in a way that discussions of Type 5 or Type 6 civilizations cannot be. There is a thread in archaeological and historical speculation that connects to the Kardashev framework in an interesting, if less rigorous way. The question occasionally raised is whether evidence exists for advanced civilizations that predate recorded human history. The Great Pyramid at Giza is one of the structures most frequently cited in this context. It stands approximately 138 meters tall and was constructed from approximately 2.3 million stone blocks, each weighing an average of 2.5 metric tons. The precision of its construction is genuinely remarkable. The four sides are aligned to the cardinal directions with an accuracy of within a fraction of a degree. The base is level to within about 2.1 centimeters across its entire 230-meter width. Mainstream archaeology holds that the pyramid was built around 4,500 years ago using organized labor, copper tools, wooden sledges, and sophisticated logistical systems. The workforce involved numbered in the tens of thousands, working over a period of approximately 20 years. Recent archaeological evidence, including administrative records discovered near the site, papyrus documents, and workers' villages, has substantially strengthened this interpretation. We are not entirely without documentation of how the pyramids were built, but the engineering achievement remains genuinely impressive by any standard, and it raises legitimate questions about the organizational and technological capabilities of ancient civilizations. These questions are best answered through careful archaeology and engineering analysis, not through speculation about vanished advanced civilizations. The evidence that exists points clearly to human ingenuity and labor as the explanation for ancient megastructures, including the pyramids, Stonehenge, Machu Picchu, and the Nazca lines. These are extraordinary accomplishments that do not require extraordinary explanations beyond the creativity, organization, and determination of the people who built them. The broader question raised by the Kardashev Scale is not about ancient mystery, but about the future trajectory of civilization. The scale makes explicit something that is easy to overlook in day-to-day scientific and political discussion. The long-term sustainability and expansion of any civilization is fundamentally an energy problem. Get the energy right, and many other things become possible. Fail to secure sustainable energy at scale, and advancement stalls. For humanity specifically, the transition from Type 0 to Type 1 is the critical near-term challenge. This is not a theoretical or distant concern. It is happening now, in real time. The global shift toward renewable energy, the development of nuclear fusion research programs, the construction of large-scale battery storage systems, the electrification of transportation, all of these are steps, however incremental, in the direction of Type 1 energy infrastructure. The obstacles are political, economic, and engineering challenges rather than fundamental physical barriers. The dangers associated with each level of the Kardashev scale are also worth considering carefully. A Type 0 civilization, which is what we currently are, faces the risk that it will consume its planet's resources faster than it can develop the technology to replace or expand them. Fossil fuel depletion, climate disruption from greenhouse gas emissions, soil degradation, freshwater scarcity, all of these are Type 0 problems. They arise directly from our current position on the scale, advanced enough to exploit planetary resources rapidly, but not yet advanced enough to manage them sustainably at global scale. A Type 1 civilization faces a different set of risks. Having mastered planetary energy, it might deplete the reserves available on its home planet and nearby neighbours before developing the capability to reach its parent star. Or it might develop technologies with destructive potential commensurate with its energy access, weapons, or other tools capable of civilizational scale destruction. The history of human technology suggests that destructive applications of new energy sources often follow closely behind their productive applications. Nuclear weapons arrived alongside nuclear power. This pattern does not become less relevant as energy scales increase. A Type 2 civilization faces the eventual, inevitable exhaustion of its parent star. All stars have finite lifespans, determined by their mass and composition. Our own sun will exhaust its hydrogen fuel in approximately 5 billion years, at which point it will expand into a red giant and eventually collapse into a white dwarf. A Type 2 civilization dependent on its parent star must develop either stellar engineering to extend the star's life or the capability to migrate to new stellar energy sources before the original star fails. Neither of these is impossible, in principle, but both require extraordinary long-term planning and technological capability. A Type 3 civilization faces the ultimate long-term energy challenge, the heat death of the universe. As stars burn out over trillions of years, the total available energy for doing work decreases irreversibly. A civilization that has colonized an entire galaxy must eventually confront the question of what happens when the galaxy's stars finish burning. Theoretical proposals for extending a civilization's energy access beyond the stellar epoch include harvesting energy from rotating black holes using the Penrose process, extracting energy from the quantum vacuum, or utilizing dark energy. None of these have been demonstrated to be practically achievable, but they represent the kind of long-term physical thinking that a genuinely advanced civilization would eventually need to engage with. The question of where exactly humanity is headed on this scale is not answerable with precision. There are too many variables: geopolitical stability, the pace of technological development, the outcome of the global energy transition, the possibility of existential risks from climate change, pandemics, or emerging technologies. What the Kardashev Scale provides is not a guaranteed roadmap, but a framework for understanding the relationship between where we are now and where we might eventually be. One of the most valuable insights from this framework is that the gap between Type 0 and Type 1, the gap that humanity is currently in the middle of crossing, is arguably the most dangerous part of the journey. We have developed technologies powerful enough to cause existential harm, but we have not yet developed the social, political, and institutional systems needed to manage those technologies reliably at global scale. We are in an awkward transitional phase, too advanced to be vulnerable only to natural threats, but not yet advanced enough to have secured our long-term survival. The physicist Carl Sagan, who was one of the most prominent popularizers of Kardashev's ideas, framed this transition in terms of a species reaching adolescence. Adolescence is the phase in human development characterized by the acquisition of new and powerful capabilities before the wisdom and social structures needed to use them responsibly have fully matured. The analogy is imperfect, as all analogies are, but it captures something real about the current situation of our species. We have nuclear weapons. We have the ability to engineer pathogens. We have artificial intelligence systems whose long-term behavior and capabilities are not yet fully understood. We are using all of these technologies while still organized into competing nation-states with limited mechanisms for global coordination. Getting through this phase without catastrophic self-inflicted damage is the central challenge of our current moment in history. The Kardashev Scale suggests that if we do get through it, the trajectory on the other side is potentially extraordinary. A unified Type 1 civilization, having solved its energy and coordination problems, would be positioned to begin the process of expanding beyond its home planet in a systematic and sustainable way. The steps from there toward Type 2 and eventually Type 3 would unfold over geological timescales, but they would be steps taken from a position of security rather than precariousness. The scientific study of the Kardashev framework has also generated productive research programs in several areas. The search for technosignatures in astronomical data has become a recognized field, with observations being conducted using radio telescopes, optical telescopes, and infrared space observatories. The SETI Institute, the Breakthrough Listen Initiative, and various university research programs are actively scanning the sky for signals that might indicate the existence of technologically advanced civilizations elsewhere in the galaxy. So far, no confirmed detection has been made, but the sensitivity of these searches has increased dramatically over the past few decades, and the amount of sky being surveyed is growing. Astronomers have also developed more sophisticated models for what technosignatures from different types of civilizations might look like. A Type 1 civilization might produce radio leakage from its communications networks, industrial pollution, detectable in its planet's atmospheric spectrum, or orbital signatures from large space stations. A Type 2 civilization might produce the infrared excess associated with a Dyson Sphere or partial Dyson shell. A Type 3 civilization might produce something detectable at galactic scales, though what exactly that signature would look like is harder to predict because we have no examples to study. The lack of detected signals so far has not discouraged the research community. The universe is old and large, and our searches have covered only a tiny fraction of it in any systematic way. We have been broadcasting radio signals for roughly 100 years, a distance of 100 light years in all directions. The galaxy is about 100,000 light years in diameter. Our radio bubble is a small island in an enormous ocean, and we have only recently developed the technology to look for signals from other islands. Future telescope projects, including next-generation radio arrays and large space-based observatories, will extend the reach and sensitivity of these searches significantly. Missions designed to characterize the atmospheres of planets orbiting other stars will search for biosignatures, chemical indicators of life, and potentially technosignatures as well. The coming decades will see a dramatic expansion in our ability to survey the sky for signs of life and technology. There is also a theoretical effort underway to better characterize the minimum energy requirements for different kinds of civilizations and to understand what physical constraints might limit or shape the development of advanced civilizations. These efforts draw on thermodynamics, information theory, complexity science, and cosmology. They represent an attempt to do for the Kardashev framework what physics has done for engineering: replace qualitative guesses with quantitative predictions grounded in physical law. One area of active theoretical interest is the relationship between information processing and energy. A civilization's capability is not just about the total energy it can access, but about how efficiently it can convert energy into useful computation and information processing. Researchers studying this relationship have proposed that the ultimate limits on computation are set by thermodynamic constraints. The relationship between information erasure and heat dissipation, first worked out by physicist Rolf Landauer in 1961. A sufficiently advanced civilization would need to think carefully about the thermodynamic efficiency of its computing infrastructure, not just the total energy available to it. Another area of interest is the relationship between energy access and the risk of catastrophic outcomes from advanced technologies. Some researchers have proposed that there may be a window of maximum danger in the development of any technological civilization, a period after which destructive technologies become accessible, but before robust global governance mechanisms are in place to prevent their misuse. If this window is short, and if civilizations typically navigate it successfully, the galaxy might be full of advanced civilizations. If the window is long or difficult to navigate, it might be the filter that prevents most civilizations from reaching Type 1. Understanding where we are in relation to that potential filter and how to navigate it successfully is arguably the most important scientific and political question of the current era. The Kardashev Scale gives us one way to locate ourselves in a larger framework. We are a species that has reached the edge of its initial energy regime, capable of seeing the outlines of a much larger one, but not yet certain that it will make the transition successfully. What remains genuinely open in the science is extensive. We do not know how common life is in the universe. We do not know how common intelligence is among living systems. We do not know how frequently intelligence leads to technology. We do not know whether any civilization has ever successfully crossed the transition from Type 0 to Type 1, let alone beyond that. We do not know what the universe would look like if it were populated by multiple Type 3 civilizations. We do not know whether the physical constraints of spacetime place an ultimate ceiling on what is possible, or whether the upper limits of the Kardashev Scale, types 4, 5, and beyond, represent real possibilities or theoretical fictions. What we do know is that energy is the universal currency of capability. Every civilization, wherever it might exist in the universe, faces the same fundamental challenge that we face: how to sustainably access enough energy to do what it needs to do, without destroying the systems it depends on in the process. The Kardashev Scale is a way of measuring how well a civilization has answered that challenge. And by that measure, we are just getting started. Research continues on multiple fronts simultaneously. Astronomers are surveying tens of thousands of stars with improving instruments, looking for anomalies that might indicate artificial structures. Physicists are developing better theoretical models of what advanced civilizations might look like based on physical first principles. Engineers are working on the technologies, fusion energy, large-scale solar arrays, advanced battery storage, orbital solar power, that could move us meaningfully toward Type 1 within the lifetimes of people alive today. Astrobiologists are studying the conditions that give rise to life and intelligence, trying to estimate whether our galaxy is likely to be occupied by other technological civilizations, or whether we are exploring it more or less alone. All of these research programs are connected by the same underlying question: how far can technology go, and has anyone out there gone further than we have? The Kardashev Scale does not answer that question, but it gives us a precise and physically grounded way to ask it. That, for a question of this magnitude, is no small thing. The next 100 years will be telling. If we successfully navigate the energy transition and build a genuinely sustainable global civilization, we will be on track towards Type 1. If we develop robust methods for detecting biosignatures and technosignatures in the atmospheres and orbits of distant planets, we may learn something definitive about whether we are alone. And if fusion power, space-based solar energy, or some currently unforeseen technology provides the energy density needed to move humans through the solar system efficiently, the first steps toward Type 2 will be within reach of civilizations that come after us. The scale is not a promise, it is a map of the possible. And like all maps, it is most useful not as a guarantee of arrival, but as a guide for figuring out which direction to walk. It is worth spending more time on the precise engineering that separates our current civilization from a genuine Type 1, because the details reveal both how achievable the goal is and how much work remains. Consider the global electricity grid as it currently exists. In 2023, global electricity generation reached approximately 30,000 terawatt-hours for the full year. Most of that electricity was generated from fossil fuels, primarily coal and natural gas, with nuclear, hydropower, wind, and solar contributing increasing but still minority shares. The generation was not coordinated globally. It was managed through hundreds of largely independent national and regional grid systems, each balanced separately using local generation resources. Electricity crosses borders through a limited number of high-voltage interconnections, but the majority of power consumption in any given country is supplied by generation within that country or its immediate neighbours. A Type 1 civilization would look fundamentally different. The generation mix would be dominated by sources with no fuel cost and no carbon emissions, primarily solar, wind, and fusion, with storage technologies and demand management providing stability. The grid itself would be genuinely global, with high-voltage direct current lines spanning continents and undersea cables connecting them. The generation and consumption of power would be managed in real time by automated systems with far greater computational intelligence than current grid management software. And the total power throughput would be roughly 1,000 times what it is today, reflecting both the expanded energy access of Type 1 status and the elimination of the enormous inefficiencies in our current energy conversion chain. That 1,000 times increase in power throughput is achievable without any physics beyond what we already know. Solar irradiance at Earth's surface averages about 170 watts per square meter after accounting for day-night cycles, weather, and latitude. To supply 10 quadrillion watts, the order of magnitude required for Type 1 from surface solar alone would require covering roughly 60 million square kilometers with solar panels at current efficiency levels. That is about 12% of Earth's land area, or roughly the size of the combined land area of Russia and Canada. Spread over a century or two, converted progressively as manufacturing scales up and costs fall, this is a large but not fundamentally impossible engineering project. The efficiency of solar panels has been increasing steadily through research improvements. Current commercial panels typically convert between 20 and 23% of incident sunlight to electricity. Laboratory cells have achieved efficiencies above 47% using multi-junction designs. As manufacturing technology improves and higher efficiency designs move from laboratory to commercial production, the land area required for a given power output decreases correspondingly. Advances in transparent solar cells, building integrated photovoltaics, and floating solar installations on water surfaces all expand the potential area available without competing with agriculture or natural habitats. Wind energy has a similar profile. Modern wind turbines have capacities of up to 15 megawatts per turbine for offshore installations, and the capacity factor, meaning the fraction of their rated power that they generate on average, has been improving steadily as turbine design, siting, and forecasting have advanced. Offshore wind has the advantage of stronger and more consistent wind resources than most onshore locations, and does not compete for land area. The world's continental shelf areas, where water is shallow enough for fixed-bottom offshore wind installations, represent an enormous resource. For deeper water, floating offshore wind platforms are being developed, further expanding the accessible resource. The intermittency of solar and wind, the fact that they generate power only when the sun shines or the wind blows, is often cited as a fundamental limitation. In reality, it is an engineering and economic challenge rather than a physics one. Multiple approaches to managing intermittency are being developed in parallel. Battery storage systems using lithium-ion chemistry today, and potentially other chemistries in the future, can store excess generation for hours to days. Pumped hydropower, which stores energy by pumping water uphill and releases it by letting the water flow back through turbines, can store energy for days to weeks, and is already the dominant, large-scale energy storage technology globally. Hydrogen produced by electrolysis of water using surplus renewable electricity can be stored and used as fuel when needed, providing seasonal storage on timescales of months. And the geographic complementarity of solar and wind across a global grid, as noted earlier, reduces the storage requirement by allowing regions with surplus generation to supply regions with deficit. The combination of these approaches means that a global energy system based predominantly on variable renewable sources is technically feasible. The economic challenge is building the infrastructure. The political challenge is coordinating across jurisdictions. These are significant but not insurmountable. The rapid cost reductions in solar panels and wind turbines over the past 15 years, which have made them the cheapest sources of new electricity generation in most of the world, have transformed the economics of the energy transition in ways that were not anticipated even 10 years ago. The trajectory suggests that the economic incentives for transitioning to clean energy will continue to strengthen even without policy intervention, simply because the technology is becoming cheaper, faster than fossil fuel extraction. The electrification of transportation is a complementary process. Electric vehicles are already cheaper to operate than internal combustion vehicles in most markets, and upfront purchase prices are declining toward parity. As the electricity supply becomes cleaner, the climate benefit of electric vehicles increases. The electrification of heating through heat pumps, which move heat from air or ground into buildings rather than generating it by burning fuel, offers similar efficiency gains in the building sector. Together, electrification of transport and heating, combined with the decarbonisation of electricity generation, addresses the majority of current greenhouse gas emissions from energy use. The remaining hard-to-decarbonise sectors include heavy industry such as steel and cement production, long-haul aviation, and maritime shipping. These sectors are more challenging because they require either high-temperature processes that are difficult to electrify or fuels with high energy density for long-distance travel. Research into green hydrogen, synthetic fuels produced using renewable electricity, and novel production processes for steel and cement using electricity rather than carbon-based reducing agents is progressing. Though these technologies are not yet economically competitive at scale, the broader point is that the transition to a Type 1 civilization is a project of enormous scope, but not of mysterious character. We know what needs to be done at a technical level. We know how to do most of it. The remaining technical challenges are being actively worked on by large research communities around the world. The questions of pace and priority are primarily social, economic, and political, rather than scientific. This is actually an encouraging observation. Scientific and technical unknowns are hard to accelerate on demand because discovery follows its own internal logic and cannot simply be commanded to occur faster. But social and political challenges, though genuinely difficult, are responsive to human choices in a way that natural phenomena are not. We can choose to prioritize funding for energy research. We can choose to implement carbon pricing that reflects the true cost of emissions. We can choose to strengthen international cooperation on the energy transition. We can choose to accelerate the deployment of proven technologies through public investment and favorable regulatory frameworks. These are choices in the domain of human agency, not mysteries waiting to be solved. The Kardashev Scale, viewed in this light, is not primarily a taxonomy of exotic hypothetical civilizations. It is a map of where we are and where we need to go, grounded in the physical science of energy. The path from our current 0.73 to a full Type 1 passes through problems that are hard but known, using approaches that are promising but incomplete, requiring coordination that is challenging but not unprecedented. The history of the past 250 years, since the beginning of the Industrial Revolution, is a history of energy transitions accomplished in the face of enormous social and economic inertia. Each transition, from wood to coal, from coal to oil, from oil to natural gas, from all of these to the current diversifying mix of renewables and nuclear, has been driven by a combination of technological development, economic incentive, and policy response to emerging challenges. The current transition from fossil fuels to clean energy is the largest in scope and the most urgent in timeline of any that has come before. But it is also the one with the most sophisticated scientific understanding behind it, the most globally coordinated policy attention, and the most rapid technology cost reduction. Whether these advantages will be sufficient to complete the transition on the timescale needed to avoid the worst consequences of climate change and to put humanity on a trajectory toward Type 1 status is the defining question of this generation of civilization. Future generations, if the transition succeeds, will look back on this period as the beginning of humanity's genuine ascent on the Kardashev scale, the point at which a species that had been burning ancient carbon for 2 centuries began to build the energy infrastructure of a planetary civilization. The tools they will use were built in this era. The scientific understanding they will apply was developed in this era. The institutions they will work within were shaped by choices made in this era. What they inherit and what trajectory they continue is determined in large part by what we do now. The Kardashev Scale was conceived as a tool for thinking about civilizations across the galaxy, but it is also a mirror. It reflects back to us a precise and quantitative picture of where we stand in the space of all possible technological civilizations, and it makes clear that we are very early in the story. The universe is large, the energy available is enormous, and the physics permits civilizations of extraordinary capability. Whether we are among the civilizations that reach those heights, or whether we remain at the beginning of the scale, is a question whose answer is being written in the choices, investments, and institutions of our own time. That is where the science leaves us. With knowledge of what is possible, uncertainty about what will happen, and responsibility for what we choose to do. It is an uncomfortable position in some ways, because it removes the comfortable fatalism of assuming the future will simply unfold according to forces beyond our control. It replaces that comfort with the more demanding truth that the trajectory of our civilization is genuinely contingent on decisions being made by people alive today. But it is also an empowering position, because it means that the outcome is not fixed. It means that the work matters. It means that every advance in energy technology, every improvement in global governance, every expansion of scientific understanding contributes to a trajectory whose endpoint is not yet determined. The universe is not indifferent to us in the sense of having preferences about our choices, but it does have structure. It has laws. It has energy in quantities we have barely begun to access. And it has a history that is 4.6 billion years old for our planet and 13.8 billion years old for the universe itself, compared to which our civilization is barely a flash. The Kardashev Scale is a way of seeing that flash in context and understanding that the context extends far beyond where we currently stand. We are at 0.73. The scale runs to type 3 and beyond. The physics is known, the engineering is hard but tractable. The social challenges are the most difficult of all, and the outcome depends on us. The energy available to a Type 1 civilization from its home star alone is staggering by any measure. Earth intercepts roughly 1.7 times 10 to the 17th watts of solar power, or about 170 quadrillion watts. Of that, our current global civilization uses approximately 18.4 terawatts, which is about 18.4 trillion watts. To put that in proportion, we currently use roughly 1/10,000th of the solar energy that reaches Earth's surface. A true Type 1 civilization would be using all of it, or close to all of it, through some combination of solar farms covering continents, orbital solar collection systems, beaming power to the surface, atmospheric energy harvesting, and geothermal tapping of the planet's internal heat. The difference between where we are and where a Type 1 civilization is represents more than just a numbers gap. It represents a qualitative transformation in how civilization relates to its environment. Today, human civilization is a consumer of natural resources. We extract materials and energy from the environment, process them, use them, and discard waste products back into the environment. A Type 1 civilization is something closer to a planetary manager. It actively shapes its environment rather than simply reacting to it. It does not just consume energy, it optimizes the flow of energy through its planetary system. This shift from consumer to manager is reflected in specific technologies that we can already see in early development. Smart electrical grids that balance supply and demand in real time are a primitive prototype of the planetary energy management systems a Type 1 civilization would operate. Carbon capture technology that removes waste products from the atmosphere is a primitive prototype of the planetary atmospheric management systems a Type 1 civilization would routinely use. Geoengineering proposals to manage solar radiation through artificial aerosols or orbital reflectors are early, untested sketches of the weather and climate management capabilities that would be routine at Type 1. We are not there yet, but we can see the direction clearly. The concept of planetary engineering deserves particular attention because it represents a threshold that no previous civilization in human history has approached. Engineering at the scale of a single city or even a nation is well within our historical experience. Engineering at planetary scale is categorically different. It requires understanding and managing systems so complex that our current models and computational tools are only beginning to approach the necessary fidelity. Climate modeling is the closest thing we currently have to planetary scale systems engineering, and it remains imperfect. Getting from where we are now to the level of planetary management that defines a Type 1 civilization will require not just better technology, but fundamentally better science, better understanding of complex systems, feedback loops, and long-term dynamics than we currently possess. The role of computing in this transition cannot be overstated. Every advance in planetary scale engineering depends on our ability to model, predict, and optimize extremely complex systems. The computational demands of managing a Type 1 civilization's energy grid, atmospheric systems, and resource flows would be vastly larger than anything current systems can handle. The development of more powerful computing, whether through classical improvements in semiconductor technology, quantum computing, neuromorphic computing, or something not yet invented, is not separate from the Kardashev transition. It is integral to it. You cannot manage a planet without computers powerful enough to model it. This connection between information processing and civilization scale is one of the deepest insights that emerges from careful thinking about the Kardashev framework. Information and energy are not separate dimensions of civilizational advancement. They are coupled. Every increase in energy access requires more sophisticated information processing to manage it effectively. Every advance in information processing enables access to new energy sources and more efficient use of existing ones. The two scale together, and a civilization that advances in one without the other will hit bottlenecks quickly. Consider the development of electrical power grids. The invention of practical electricity generation in the late 19th century was followed immediately by the challenge of distributing that electricity efficiently across large areas. Solving the distribution problem required telegraph and telephone communication networks to coordinate the grid in real time. As grids grew larger and more complex, more sophisticated control systems were needed. Today, managing a national electrical grid is a continuous real-time optimization problem of extraordinary complexity, handled by sophisticated software systems monitoring millions of data points simultaneously. The same pattern will repeat at planetary scale and, eventually, at stellar scale. The energy infrastructure and the information infrastructure advance together because neither can function without the other. Looking at the history of energy transitions on Earth gives a useful sense of the pace and character of these changes. The shift from wood to coal as the primary energy source for industrial civilization took roughly a century in most developed nations. The shift from coal to oil and natural gas took roughly another century. Each transition involved not just a change in fuel type, but a wholesale reorganization of economic systems, infrastructure, geopolitics, and daily life. The current transition toward renewable energy and electrification is underway but is not complete, and its pace and ultimate shape are still being determined by economic, political, and technological forces that interact in complex ways. The key difference between historical energy transitions and the transition to Type 1 civilization is one of intentionality. Past energy transitions happened largely as the emergent result of economic incentives and technological opportunism. Individual actors made decisions based on local information and short-term incentives, and the transition emerged from the aggregate of those decisions over time. The transition to Type 1, if it happens, will need to be more deliberate. It will require global coordination to manage shared resources like the atmosphere and the oceans, to prevent technological risks that no single nation can manage alone, and to ensure that the benefits of advanced energy technology are distributed in ways that maintain social stability rather than generating the kind of extreme inequality that leads to conflict. Whether humanity is capable of that kind of deliberate, globally coordinated long-term planning is genuinely uncertain. The history of international cooperation on climate change, nuclear proliferation, and pandemic response offers a mixed record. There are cases of successful global coordination. The Montreal Protocol to protect the ozone layer is often cited as a positive example, and cases of failure. The coming decades will provide evidence about which of these patterns is more characteristic of our species when the stakes are highest. The Fermi paradox casts a long shadow over optimistic thinking about the Kardashev scale. Enrico Fermi, the physicist, is reported to have asked during a lunch conversation in 1950 the question that now bears his name: if advanced civilizations are possible, and if the universe is old enough for them to have developed, where is everybody? The universe is approximately 13.8 billion years old. The Milky Way galaxy has been forming stars for roughly 13 billion years. Many stars in our galaxy are significantly older than our own sun, which is only 4.6 billion years old. If even a small fraction of those older stars hosted planets that developed intelligent life, there has been time for civilizations to arise, develop advanced technology, and spread across significant portions of the galaxy before our sun even formed. The silence of the cosmos, the absence of obvious signals or artifacts from advanced civilizations, requires an explanation. The Kardashev scale, by clarifying what advanced civilizations should be capable of and what signatures they should produce, sharpens the puzzle considerably. If a Type 3 civilization exists anywhere in our galaxy, it should be detectable. The energy flows associated with managing an entire galaxy's stellar population would be enormous, and some fraction of that energy should escape as detectable radiation. The fact that we see nothing of the kind either means that Type 3 civilizations do not exist, or that they exist but are undetectable to us for reasons we do not understand, or that there is something about the development of technology that prevents civilizations from reaching Type 3. The last possibility, the Great Filter hypothesis, is the one that carries the most weight for thinking about our own future. If most civilizations that develop technology fail to reach high levels of the Kardashev scale, the question is whether that failure point is in our past or our future. If the filter is behind us, if the reason Type 3 civilizations are rare is that the origin of life or the origin of intelligence are extremely unlikely events, then our situation is actually quite hopeful. We have already passed the hard part, and the path to advanced civilization, while long and difficult, may be open to us. If the filter is ahead of us, if most civilizations destroy themselves or collapse before reaching Type 2 or Type 3, then the absence of detectable civilizations is a warning about our own future rather than evidence of our past good fortune. The honest answer is that we do not know which scenario is correct. We do not have enough data about the frequency of life and intelligence in the universe to determine whether we are unusual survivors or typical examples. This is part of what makes the search for life elsewhere in the universe not just scientifically interesting, but genuinely important for understanding our own prospects. If we discover that life is common, and intelligence is common, and technology is common, the Fermi paradox becomes sharper and more alarming. Where are all those civilizations? If we discover that life, or intelligence, or technology is extraordinarily rare, the silence of the cosmos becomes less mysterious, and our own rarity becomes more striking. Either discovery would be one of the most significant scientific results in human history. The investment in the infrastructure for making that discovery, space telescopes capable of characterizing planetary atmospheres, radio telescope arrays sensitive enough to detect artificial signals from nearby stars, next-generation observatories scanning for infrared technosignatures, is justified both by the scientific importance of the question and by what the answer might tell us about our own trajectory. There is also a dimension of the Kardashev framework that applies not just to civilizations as a whole, but to the decisions made by individuals, institutions, and governments in the present. The choice to invest in renewable energy rather than continuing to rely on fossil fuels is, in the language of the Kardashev framework, a choice about whether to continue toward Type 1 or to remain stuck near Type 0. The choice to invest in fusion research, in orbital solar power, in global coordination mechanisms for managing planetary systems, all of these are choices about the direction of civilizational development in the large-scale sense. One of the most important contributions of the Kardashev framework to public thinking is that it provides a context for evaluating short-term decisions against long-term consequences. It is easy to think about energy policy as a matter of economics and near-term national interest. The Kardashev Scale reminds us that energy policy is also a matter of civilizational trajectory. Decisions made in the next few decades about energy infrastructure will determine whether humanity is on a path toward Type 1 or whether we remain in a prolonged and increasingly unstable Type 0 phase that risks ending badly. The framework also highlights an asymmetry that is easy to miss in short-term political debate. The costs of transitioning towards sustainable, expanding energy systems are real but bounded. The costs of failing to make that transition, collapsing back into conflict and scarcity before the transition is complete, are potentially catastrophic and much harder to recover from. A civilization that successfully reaches Type 1 can address problems that are currently intractable. A civilization that fails to reach Type 1 may not get a second chance. Scientists working in fields adjacent to the Kardashev framework tend to share a cautious optimism about humanity's prospects. The physical barriers to Type 1 are not insurmountable. We understand the relevant physics well. We have the basic technologies in prototype form. The challenges are primarily social, political, and economic rather than physical. That is both encouraging because those challenges are in principle more tractable than physical ones, and discouraging because our track record on global coordination and long-term planning is uneven. What the scientific community is increasingly clear about is that the question of civilizational advancement is not separate from questions about sustainability, governance, and the management of existential risk. These domains, which are sometimes treated as distinct fields with different methodologies and different communities of practice, are actually deeply connected. A civilization cannot advance on the Kardashev scale without solving its sustainability problems. And solving its sustainability problems requires exactly the kind of planetary scale coordination and management that defines the transition to Type 1. As observational astronomy becomes more powerful, the coming decades will offer new data on questions that are currently unanswerable. The James Webb Space Telescope is already providing unprecedented detail about the atmospheres of planets orbiting other stars. Future missions will extend this capability to smaller, potentially habitable planets and will search for chemical signatures that might indicate the presence of life. The Vera Rubin Observatory, which is completing its construction, will survey the night sky with a cadence and depth that will generate new data on stellar variability and unusual astronomical objects, potentially including candidates for artificial structures. Planned large radio telescope arrays will extend the search for artificial signals to much larger numbers of nearby stars. All of this observational activity is driven by the same fundamental question that Kardashev's scale helps to frame. Are we alone in our level of development, or does the universe contain others who have gone further? The answer to that question, whatever it turns out to be, will reshape our understanding of our place in the cosmos, and, potentially, our understanding of our own future. For now, what we know is this: we are an early-stage technological civilization at a critical transition point. The physical principles that define the path forward are well understood. The energy sources available to us at higher levels of the scale are real and accessible in principle. The obstacles in our immediate path are solvable with existing or near-term technology. Whether we solve them in time, and whether we do so in a way that maintains a stable and functional global society through the transition, depends on decisions being made now and in the years immediately ahead. The Kardashev Scale does not tell us that we will succeed. It tells us what success would look like, and it gives us a way to measure our progress toward it. That is, ultimately, what a good scientific framework does. Not guarantee outcomes, but clarify the map. It is worth spending more time on the precise engineering that separates our current civilization from a genuine Type 1, because the details reveal both how achievable the goal is and how much work remains. Consider the global electricity grid as it currently exists. In 2023, global electricity generation reached approximately 30,000 terawatt-hours for the full year. Most of that electricity was generated from fossil fuels, primarily coal and natural gas, with nuclear, hydropower, wind, and solar contributing increasing but still minority shares. The generation was not coordinated globally. It was managed through hundreds of largely independent national and regional grid systems, each balanced separately using local generation resources. Electricity crosses borders through a limited number of high-voltage interconnections, but the majority of power consumption in any given country is supplied by generation within that country or its immediate neighbours. A Type 1 civilization would look fundamentally different. The generation mix would be dominated by sources with no fuel cost and no carbon emissions, primarily solar, wind, and fusion, with storage technologies and demand management providing stability. The grid itself would be genuinely global, with high-voltage direct current lines spanning continents and undersea cables connecting them. The generation and consumption of power would be managed in real time by automated systems, with far greater computational intelligence than current grid management software. And the total power throughput would be roughly 1,000 times what it is today, reflecting both the expanded energy access of Type 1 status and the elimination of the enormous inefficiencies in our current energy conversion chain. That 1,000 times increase in power throughput is achievable without any physics beyond what we already know. Solar irradiance at Earth's surface averages about 170 watts per square meter after accounting for day-night cycles, weather, and latitude. To supply 10 quadrillion watts, the order of magnitude required for Type 1 from surface solar alone would require covering roughly 60 million square kilometers with solar panels at current efficiency levels. That is about 12% of Earth's land area, or roughly the size of the combined land area of Russia and Canada. Spread over a century or two, converted progressively as manufacturing scales up and costs fall, this is a large but not fundamentally impossible engineering project. The efficiency of solar panels has been increasing steadily through research improvements. Current commercial panels typically convert between 20 and 23% of incident sunlight to electricity. Laboratory cells have achieved efficiencies above 47% using multi-junction designs. As manufacturing technology improves and higher efficiency designs move from laboratory to commercial production, the land area required for a given power output decreases correspondingly. Advances in transparent solar cells, building integrated photovoltaics, and floating solar installations on water surfaces all expand the potential area available without competing with agriculture or natural habitats. Wind energy has a similar profile. Modern wind turbines have capacities of up to 15 megawatts per turbine for offshore installations, and the capacity factor, meaning the fraction of their rated power that they generate on average, has been improving steadily as turbine design, siting, and forecasting have advanced. Offshore wind has the advantage of stronger and more consistent wind resources than most onshore locations, and does not compete for land area. The world's continental shelf areas, where water is shallow enough for fixed-bottom offshore wind installations, represent an enormous resource. For deeper water, floating offshore wind platforms are being developed, further expanding the accessible resource. The intermittency of solar and wind, the fact that they generate power only when the sun shines or the wind blows, is often cited as a fundamental limitation. In reality, it is an engineering and economic challenge rather than a physics one. Multiple approaches to managing intermittency are being developed in parallel. Battery storage systems using lithium-ion chemistry today, and potentially other chemistries in the future, can store excess generation for hours to days. Pumped hydropower, which stores energy by pumping water uphill and releases it by letting the water flow back through turbines, can store energy for days to weeks and is already the dominant, large-scale energy storage technology globally. Hydrogen produced by electrolysis of water using surplus renewable electricity can be stored and used as fuel when needed, providing seasonal storage on timescales of months. And the geographic complementarity of solar and wind across a global grid reduces the storage requirement by allowing regions with surplus generation to supply regions with deficit. The combination of these approaches means that a global energy system based predominantly on variable, renewable sources is technically feasible. The economic challenge is building the infrastructure. The political challenge is coordinating across jurisdictions. These are significant, but not insurmountable. The rapid cost reductions in solar panels and wind turbines over the past 15 years, which have made them the cheapest sources of new electricity generation in most of the world, have transformed the economics of the energy transition in ways that were not anticipated even 10 years ago. The trajectory suggests that the economic incentives for transitioning to clean energy will continue to strengthen even without additional policy intervention, simply because the technology is becoming cheaper, faster than fossil fuel extraction. The electrification of transportation is a complementary process. Electric vehicles are already cheaper to operate than internal combustion vehicles in most markets, and upfront purchase prices are declining toward parity. As the electricity supply becomes cleaner, the climate benefit of electric vehicles increases. The electrification of heating through heat pumps, which move heat from air or ground into buildings rather than generating it by burning fuel, offers similar efficiency gains in the building sector. Together, electrification of transport and heating, combined with the decarbonisation of electricity generation, addresses the majority of current greenhouse gas emissions from energy use. The remaining hard-to-decarbonise sectors include heavy industry such as steel and cement production, long-haul aviation, and maritime shipping. These sectors are more challenging because they require either high-temperature processes that are difficult to electrify or fuels with high energy density for long-distance travel. Research into green hydrogen, synthetic fuels produced using renewable electricity, and novel production processes for steel and cement using electricity rather than carbon-based reducing agents is progressing, though these technologies are not yet economically competitive at scale. The broader point is that the transition to a Type 1 civilization is a project of enormous scope but not of mysterious character. We know what needs to be done at a technical level. We know how to do most of it. The remaining technical challenges are being actively worked on by large research communities around the world. The questions of pace and priority are primarily social, economic, and political, rather than scientific. This is actually an encouraging observation. Scientific and technical unknowns are hard to accelerate on demand because discovery follows its own internal logic and cannot simply be commanded to occur faster. But social and political challenges, though genuinely difficult, are responsive to human choices in a way that natural phenomena are not. We can choose to prioritize funding for energy research. We can choose to implement carbon pricing that reflects the true cost of emissions. We can choose to strengthen international cooperation on the energy transition. We can choose to accelerate the deployment of proven technologies through public investment and favorable regulatory frameworks. These are choices in the domain of human agency, not mysteries waiting to be solved. The Kardashev Scale, viewed in this light, is not primarily a taxonomy of exotic, hypothetical civilizations. It is a map of where we are and where we need to go, grounded in the physical science of energy. The path from our current 0.73 to a full Type 1 passes through problems that are hard but known, using approaches that are promising but incomplete, requiring coordination that is challenging but not unprecedented. The history of the past 250 years since the beginning of the Industrial Revolution is a history of energy transitions accomplished in the face of enormous social and economic inertia. Each transition, from wood to coal, from coal to oil, from oil to natural gas, from all of these to the current diversifying mix of renewables and nuclear, has been driven by a combination of technological development, economic incentive, and policy response to emerging challenges. The current transition from fossil fuels to clean energy is the largest in scope and the most urgent in timeline of any that has come before. But it is also the one with the most sophisticated scientific understanding behind it, the most globally coordinated policy attention, and the most rapid technology cost reduction. Whether these advantages will be sufficient to complete the transition on the timescale needed to avoid the worst consequences of climate change and to put humanity on a trajectory toward Type 1 status is the defining question of this generation of civilization. Future generations, if the transition succeeds, will look back on this period as the beginning of humanity's genuine ascent on the Kardashev scale, the point at which a species that had been burning ancient carbon for 2 centuries began to build the energy infrastructure of a planetary civilization. The tools they will use were built in this era. The scientific understanding they will apply was developed in this era. The institutions they will work within were shaped by choices made in this era. What they inherit and what trajectory they continue is determined in large part by what we do now. One dimension of the Kardashev scale that is underappreciated in popular discussions is its relationship to information theory. In 1948, mathematician Claude Shannon published a foundational paper on information theory that established a precise mathematical relationship between information and entropy. This relationship has deep connections to thermodynamics and, ultimately, to the same energy quantities that the Kardashev scale measures. Every computation, every storage of information, every transmission of a signal requires energy. The more information a civilization processes, the more energy it needs. This means that the Kardashev scale is not just a measure of industrial or physical capability. It is also, implicitly, a measure of computational capability. A Type 1 civilization that has mastered the energy of its planet would have computational resources that dwarf our current capabilities by many orders of magnitude. The most powerful computing systems today consume megawatts of electricity. A civilization with access to tens of quadrillion watts of energy could, in principle, build computing systems with energy budgets 1 billion times larger than anything currently possible. The implications for artificial intelligence, scientific simulation, and the processing of information about the universe are difficult to overstate. A civilization at Type 1 would not just be able to perform computations faster than us, it would be able to perform computations of a fundamentally different character, modeling planetary climate systems in real time, simulating the behavior of complex biological systems at molecular resolution, processing astronomical data from millions of sensors distributed across a solar system. This computational dimension adds another layer to the Kardashev hierarchy. It suggests that the civilizations at higher levels of the scale are not just physically more powerful, they are cognitively more capable, in the sense that they can process and analyze information about the universe at a depth and breadth that lower-level civilizations cannot match. The laws of physics that govern all of these civilizations are the same, but the ability to discover, apply, and extend those laws depends on the computational and analytical resources available. The question of artificial intelligence is particularly important here. Our own civilization is currently in the early stages of developing artificial general intelligence, which, if successful, would represent a form of intelligence not constrained by the biological architecture of the human brain. The potential implications of this development for our trajectory up the Kardashev scale are enormous. An artificial intelligence capable of conducting research and engineering at superhuman levels could dramatically accelerate the pace of technological development. The same intelligence that solves fusion power might also solve the engineering of large-scale space infrastructure, the chemistry of better energy storage, and the physics of more efficient energy conversion, potentially in a very short time compared to the pace of human-only research. The coupling between energy technology and space access is one of the key leverage points for advancing up the Kardashev scale. As access to space becomes easier and cheaper, the resource base available to civilization expands from a single planet to an entire solar system. As the resource base expands, the energy infrastructure that can be built expands. As the energy infrastructure expands, the capabilities of the civilization expand. This is the self-reinforcing cycle that Kardashev was describing when he set up his scale in the first place. The James Webb Space Telescope, launched in December 2021, represents a significant advancement in our ability to study the atmospheres of exoplanets. By analyzing the spectrum of light that passes through an exoplanet's atmosphere during a transit, astronomers can identify chemical signatures. If they find combinations of gases that cannot be produced by purely geological processes, such as high concentrations of both oxygen and methane simultaneously, which would react with each other and therefore must be continuously replenished, that would be a strong indicator of biological activity. Webb has already begun returning data on exoplanet atmospheres, and the capability to detect biosignatures now exists in a way it did not before. The search for evidence of Type 2 or Type 3 civilizations elsewhere in the galaxy has become more systematic and more scientifically sophisticated in recent years. The Breakthrough Listen initiative, launched in 2015 with significant private funding, represents the most comprehensive search for extraterrestrial intelligence ever undertaken. It is using some of the world's most powerful radio telescopes to survey the 1 million nearest stars, the 100 nearest galaxies, and the entire Milky Way plane at radio frequencies, as well as conducting optical searches for laser pulses. The data volumes are enormous, and analysis requires significant computational resources. Machine learning tools have been developed to help distinguish candidate signals from the enormous amount of radio frequency interference produced by human technology and natural sources. The Fermi paradox remains unresolved. The galaxy is old enough that a civilization originating just a few billion years before us, would have had time to spread across the entire Milky Way, even at speeds far below the speed of light, and yet we see no clear evidence of other civilizations. The Great Filter hypothesis suggests that somewhere in the development from simple chemistry to a visible galactic civilization, there is a step or steps that are extremely improbable. Whether those filters are behind us in our evolutionary past or ahead of us in the challenge of managing advanced technology is one of the most important questions we could answer, because the answer determines how worried we should be about our own trajectory. Current research in astrobiology, planetary science, and evolutionary biology is beginning to provide some empirical constraints on these questions. The discovery that Mars had liquid water on its surface for billions of years raises the question of whether life began there independently. If we discover microbial fossils in Martian rocks, that would enormously increase the estimated probability that life arises wherever conditions permit. The missions planned for the ice moons of Jupiter and Saturn, particularly the Europa Clipper, and planned missions to Enceladus, will investigate environments that may harbour liquid water and chemical gradients capable of supporting life. What the Kardashev Scale ultimately offers is a sense of proportion. It places humanity in a context that makes clear both how far we have come and how much farther there is to go. We are a civilization that has learned to manipulate electricity, split atoms, send signals across the planet at the speed of light, land humans on the moon, and create machines that can perform certain cognitive tasks with remarkable efficiency. By cosmic standards, we are just getting started. Whether we continue to develop, stagnate, or collapse is not predetermined. It depends on decisions being made right now about how we manage our energy systems, our environment, our political institutions, and our scientific investment. The universe has the energy to support civilizations far beyond anything we have yet achieved. The physics permits it, the mathematics describes it, the observations are consistent with it. Whether the biology and the social evolution required to get there are also achievable is the question that our own story, still being written, will help to answer. We are at 0.73, and the scale runs far higher than we can fully imagine. Whether we continue the climb depends on us, on the choices of people alive today, on the institutions we build and the priorities we set, and on whether we prove capable of the cooperation and foresight that reaching the next level will require. The history of science offers several useful analogies for where we are in relation to the Kardashev transition. In the early 19th century, steam power was transforming manufacturing and transportation, but electricity was barely understood. A scientist in 1820 looking forward could not have predicted the internet, nuclear power, or satellite communications. Yet all of those followed, step by step, from discoveries and engineering breakthroughs that were already becoming possible in 1820. The path from where we were then to where we are now was not obvious, but it was physically possible, and it happened because generations of researchers and engineers kept pushing at the boundaries of what was known. The situation today is similar in structure, but different in scale. We can see, with reasonable scientific clarity, the outlines of what a Type 1 civilization looks like. We cannot see as clearly what comes after that, just as the scientist in 1820 could not clearly see the transistor. But we know enough physics to be confident that the energy sources needed for types 2 and 3 exist. Stars are real. Stellar energy output is measured with high precision, the theoretical basis for megastructure construction, while enormously challenging in practice, does not require any new physics beyond what we already have. The path forward is obscured by engineering challenges and social challenges, not by missing science. This is an important distinction. Science fiction often portrays advanced civilizations as requiring not just advanced engineering, but fundamentally different physics. Faster than light travel, warp drives, wormholes, and other phenomena that require violations or extensions of known physics. These are speculative possibilities, but they are not prerequisites for reaching Type 2 or 3 on the Kardashev scale. You can colonize a stellar system without faster-than-light travel. It just takes a long time. You can build a Dyson Sphere without exotic physics. It just requires enormous quantities of conventional materials and centuries of engineering. The advanced civilizations described by the Kardashev framework are not magic. They are simply what happens when known physical principles are applied at much larger scales with much greater technological sophistication. This also implies that any civilization in the universe operating under the same laws of physics that we experience faces the same basic menu of options. The sequence from Type 0 to Type 3 follows from thermodynamics and astrophysics in a way that is not specific to any particular biology or culture. A silicon-based machine intelligence, a biological species radically different from humans, or an entirely novel form of organized matter could all, in principle, traverse the same scale. What they would build, how they would communicate, and what their history would look like might be almost unimaginably alien. But the energy physics governing their development would be the same. This universality is one of the most striking features of the Kardashev framework. It suggests that if we search the universe for technosignatures, we know what physical phenomena to look for, regardless of what the civilization doing the engineering looks like. Infrared excess from Dyson spheres, anomalous stellar dimming from partially constructed megastructures, chemical technosignatures in the atmospheres of inhabited planets, radio emission patterns inconsistent with natural sources, all of these would be detectable with the right instruments, regardless of the biology or chemistry of the civilization that produced them. Physics is the universal language, and the Kardashev scale is one vocabulary within it. The search for such signatures is now entering a new era of capability. Machine learning algorithms trained on large astronomical datasets can now flag anomalous objects for human review much more efficiently than was possible even a decade ago. The total volume of astronomical data being collected by current and next-generation observatories is so large that human researchers could not possibly review it all manually. Automated analysis systems are becoming essential to the search, and they are becoming better at distinguishing natural anomalies from potentially artificial ones. One example of this approach in action is the Breakthrough Listen initiative, which is using machine learning to analyze data from radio telescope observations of nearby stars. The algorithms can identify signal patterns that deviate from known natural sources, flagging them for further investigation. So far, all flagged signals have turned out to have natural or human-made explanations, but the sensitivity and efficiency of the search continues to improve. The probability of a genuine detection, if advanced civilizations exist and are producing detectable signals, is increasing with each generation of instruments and analysis tools. Optical SETI, the search for artificial laser pulses or other optical signals from distant civilizations, has also gained momentum in recent years. A technologically advanced civilization wishing to communicate across interstellar distances might use tightly focused laser beams rather than radio waves, as lasers can achieve much higher power density at the receiver end with comparable transmitter power. Several observatories are now specifically equipped to detect nanosecond duration laser pulses that might represent intentional communication from another civilization. This search requires different instruments and different analysis techniques than radio SETI, but it is grounded in the same logic. A civilization operating at Type 2 or beyond would have the capability and possibly the motivation to send deliberately designed signals into space. The question of motivation is interesting in its own right. Why would an advanced civilization choose to communicate with or reveal itself to a less advanced one? From our perspective as the less advanced party, the question is one of pure curiosity and potential benefit. But from the perspective of a civilization that has already solved the problems we are still struggling with, the calculus might be different. There are proposals that advanced civilizations might leave deliberate markers in astronomical data specifically designed to be detectable by civilizations reaching our current technological level, a kind of cosmic lighthouse indicating the presence of others. There are also proposals that advanced civilizations might actively conceal themselves, having determined, for reasons we can only speculate about, that revealing their presence is not in their interest. We have no way to adjudicate between these possibilities without better data. What we can say with confidence is that the universe is old enough and large enough for the scenario we are contemplating to have already played out many times over, if life and intelligence are at all common. The Milky Way alone contains hundreds of billions of stars. A significant fraction of those stars have planets in their habitable zones, a fact now established beyond reasonable doubt by the Kepler and TESS space telescope missions. The fraction of habitable planets that actually develop life and the fraction of life-bearing worlds that develop technology remain deeply uncertain. But even conservative estimates, if life is even modestly common, imply that the galaxy should have been teeming with civilizations at various stages of development for billions of years. The implication of that estimate, combined with the observed silence of the cosmos, is one of the deepest unsolved puzzles in science. Either life is extremely rare, or intelligence is extremely rare, or technology is extremely rare, or something happens to technological civilizations that prevents them from becoming detectable. The Kardashev Scale helps to sharpen the puzzle because it gives us a physically grounded framework for what detectable would mean. A galaxy full of Type 3 civilizations would not look like the galaxy we observe. The fact that our galaxy does look the way we observe it is either evidence that Type 3 civilizations are extraordinarily rare, or evidence that they exist but are somehow invisible to us. One possibility that deserves mention, even though it is speculative, is that sufficiently advanced civilizations become effectively invisible to less advanced ones, not through deliberate concealment, but because of the nature of their technology. A civilization that has optimized its energy use to an extreme degree, eliminating all waste and all detectable leakage, would produce no techno-signatures accessible to an observer from outside. Advanced computation, if it becomes reversible in the thermodynamic sense, approaches arbitrarily close to zero energy dissipation per computation. A civilization that has mastered reversible computing on a large scale might be doing enormous amounts of information processing while radiating almost no detectable waste heat. Such a civilization would be, from our observational perspective, nearly indistinguishable from an uninhabited planetary system. This is a genuinely interesting possibility because it would explain the Fermi paradox without requiring either extreme rarity of life or catastrophic destruction of civilizations. It would instead suggest that the most advanced civilizations become thermodynamically quiet, which is perhaps counterintuitive from our current perspective, but makes sense if you follow the physics of information and energy to their logical conclusions. Testing this hypothesis observationally is difficult, but not impossible, and it represents the kind of creative theoretical thinking that the Kardashev framework encourages. The philosophical dimensions of the Kardashev scale are also worth acknowledging, even in a discussion primarily focused on the science. The scale invites us to locate ourselves in a much larger context than our ordinary frame of reference provides. Day-to-day political and economic discourse operates on timescales of months to decades. The Kardashev framework operates on timescales of centuries to billions of years. Bringing those two scales into contact produces a kind of cognitive vertigo that can be valuable. Decisions that seem enormously consequential in the short-term frame, election results, corporate strategies, national policy debates, look different when viewed from the perspective of civilizational trajectory. Some decisions that appear consequential in the short-term view turn out to be relatively minor in the long-term view. Others that appear minor in the short-term view, investments in basic research, early development of energy technologies, the cultivation of scientific and technical education, turn out to be pivotal for long-term trajectory. The Kardashev framework is a reminder that not all decisions have equal weight in the long term, even when they seem comparable in the short term. This is not an argument for ignoring short-term consequences. People live in the short term, and suffering is real. But it is an argument for maintaining awareness of both timescales simultaneously, which is genuinely difficult and genuinely important. The civilizations that have historically made the most durable progress have typically been those that found ways to invest in long-term capability while managing short-term challenges. The ones that have collapsed have typically been those that consumed their future to fund their present. The Kardashev Scale, in the end, is a tool for thinking about the longest arc of what is possible. It does not make predictions about specific events or guarantee any particular outcome. What it does is provide a coherent framework for understanding the relationship between energy, technology, and civilizational development across the full range of what physics allows. And within that framework, it places us precisely at an early stage with enormous potential ahead of us, facing real risks that are not inevitable but must be actively managed. The work of getting from where we are to where we could be is the work of science, engineering, governance, and human cooperation all at once. It is not primarily a problem of physics or technology, although those matter. It is primarily a problem of wisdom, whether we can be wise enough, organized enough, and far-sighted enough to navigate the transition we are in the middle of making. The universe will continue doing what it has always done, regardless of how we answer that question. Stars will continue forming and dying, galaxies will continue evolving. The physical laws that define what is possible will remain constant. Whether any civilization in any corner of this enormous cosmos has figured out how to tap into the full potential of those laws, and whether we will, remains to be seen. What is certain is that the question is worth asking, the science is worth doing, and the future is worth working toward. The history of science provides another important perspective on the Kardashev scale. Every time humanity has believed it was approaching a complete understanding of the physical world, new discoveries have revealed deeper layers of reality. In the late 19th century, some physicists believed that the major work of physics was done and only details remained to be filled in. Then came quantum mechanics, relativity, nuclear physics, particle physics, and cosmology, each revealing realms of phenomena that the previous framework could not describe. The discovery of dark matter and dark energy in the 20th century showed that the matter and energy we can directly detect make up only about 5% of the total content of the universe. The other 95% is understood only through its gravitational effects. Whether this invisible component of the universe is relevant to the energy hierarchy of the Kardashev scale is completely unknown. This pattern of discovery suggests that any estimate of the upper limits of the Kardashev hierarchy should be held loosely. We are extrapolating from current physics to ask what a much more advanced civilization might be capable of. But if current physics is incomplete, and all evidence suggests it is, then some capabilities of advanced civilizations might evolve to physical principles we have not yet discovered. This does not mean the scale is useless. It means its upper reaches should be understood as a lower bound on what might be possible, not a ceiling. The physicist Freeman Dyson articulated a useful principle in this context. He distinguished between technologies that are merely engineering challenges, requiring only the application of known physics at larger scale, and technologies that require new physics. A Dyson Sphere is an engineering challenge. Faster than light travel, if it turns out to be possible at all, would require new physics. The Kardashev hierarchy up through Type 3 is largely an engineering challenge, given our current understanding. Beyond Type 3, the extrapolations become more speculative because they begin to involve scales and phenomena where our current physics gives less guidance. What we can say with confidence is that the universe is far larger and contains far more energy than our civilization currently accesses, and that physical law does not prohibit intelligent beings from accessing an increasing fraction of that energy over time. Whether any civilization has done so, whether we will do so, and what the universe would look like to a civilization that had done so, are questions we are genuinely beginning to develop the tools to address. The radio telescopes being built in the coming decades, including the Square Kilometre Array currently under construction in South Africa and Australia, will have sensitivities many times greater than any previous instrument. They will be capable of detecting the kind of radio leakage that our own civilization currently produces from distances of tens of light years and more structured signals from much greater distances. The atmospheric characterization capabilities being developed through Webb and planned future telescopes will allow biosignature searches across hundreds of nearby star systems. The exploration of Mars and the outer solar system moons will tell us whether life has arisen independently within our own solar system. Each of these represents a genuine empirical test of hypotheses about the prevalence of life and intelligence in the universe. The answers, when they come, will be among the most significant in the history of science. If we find evidence of life elsewhere in the solar system, that tells us life is common, which raises the probability that the galaxy is inhabited. If we find no life in the solar system, despite the abundance of habitable environments Mars once had, and the subsurface oceans of the ice moons, that places a tighter constraint on the frequency of life. If SETI detects a structured signal from another star system, the entire question of where we are on the Kardashev scale relative to other civilizations becomes immediately practical rather than purely theoretical. The Kardashev scale was first proposed as a tool for the search for extraterrestrial intelligence. That remains one of its most important applications, but it has become much more than that. It is now a framework for thinking about the long-term trajectory of our own civilization, the physical limits of what technology can achieve, the relationship between energy and knowledge, and the place of intelligence in the cosmos. These are not small questions. They are among the biggest questions that a technologically capable species can ask, and we are among the first to be in a position to ask them with the precision and empirical grounding that science allows. We exist at a peculiar moment. We are advanced enough to understand the Kardashev framework and to recognize our own position in it. We are capable enough to see the path toward Type 1 and to work toward it. And we are uncertain enough about our own trajectory to take seriously both the possibility of continued progress and the possibility of failure. The scale does not resolve that uncertainty, but it clarifies what is at stake, and it reminds us that the universe is larger, older, and more energetic than our daily experience suggests, and that our civilization is very young and very small by the standards of what the universe makes possible. The next steps are clear. Develop fusion power, scale renewable energy globally, build the coordination frameworks needed for a planetary scale energy system, invest in the science needed to understand our cosmic neighborhood, search seriously for evidence of other civilizations, and take seriously the risks that could derail the transition before it is complete. None of these are simple tasks, but none of them require new physics. They require the continued application of human intelligence, cooperation, and determination to problems that are hard but tractable. In the end, the Kardashev scale asks a simple question with enormous implications. How much of the universe's energy can an intelligent civilization learn to use? The answer, as far as we can tell from current physics, is a great deal more than we currently access. Getting there is the work of the coming centuries. The scale tells us where we are. The physics tells us where we could go. The choice of whether to make the journey is ours.